Alrighty, guys. The Data Daddy here again, and as always, just want to start by saying thank you guys so much for watching the channel, and I really hope that you guys find the content useful. If you do, I'd appreciate it if you hit the like and subscribe button. And now we got that stuff out of the way. Let's talk about part 3 of the optimization series in data science. And today we will be talking about stochastic gradient descent with momentum. And we talked about SGD last time, and then gradient descent before that, and then we went over an overview. So we're kind of building more and more complexity as we go in this series. And before we go any further, again, I just want to always list my references, and I have been using the textbook or a textbook pretty closely. It's by Dr. John Miller from UGA, and it's a great textbook. I have it linked here, and it's the optimization appendix, starting on page 619. And if you've been following, at the beginning of every video, I reference it. But great textbook. I highly recommend you guys check it out. Has a ton of good stuff, not just in optimization, but really all about data science and how we can take it from the theoretical and make it into the actual. So stochastic gradient descent with momentum. Okay, we talked about SGD before, and now we just want to apply one layer of complexity, or another layer of complexity, so that we can make it even better. Because we've been talked about, we always want to. There's always a problem, or there's always a way to make things better. And in this case, stochastic gradient descent is fine, but how can we make it even better, or how can we overcome the challenges that it has? And that's what this momentum part aims to do. And so SGD, while it is wonderful and it's great and has a lot of improvement over gradient descent and saves us computation, all that stuff, it does have a known problem, and that's when basically if you think about this as gradients, well, the gradient is much steeper in one direction than the other, and these ravines, the areas where the surface curves much more steeply in one direction than the other, makes it really hard, or makes it hard for the algorithm to make any forward progress. So it just kind of sometimes can get stuck altogether and fail, or only find a local optima rather than a global optima, or it can just take a long time to navigate through these areas. So we want a way to allow this algorithm to bust through these areas where it kind of doesn't make much progress for a while. We want to give it a way to punch through those areas and really optimize quickly or converge quickly. And that's what this idea behind momentum is. As you can see, this is kind of the before, just SGD, and it iterates back and forth as we approach this local optima, and then we don't make much progress. But here, with momentum, we, in the same amount of strokes, the same amount of iterations, we'll say, we now are much further along in busting through this this local optima. Because remember, we may have, I know in the past we've used very simple examples, but these surfaces can be quite complex. So we may think we found the optimum solution, but really we've only found a local optimum solution. And we ideally we want to find the global optimum solution. So we want to bypass those local optimas and not get stuck there, so we can find the global. And that's what this algorithm helps us to do. And I took this image from this source here. I honestly don't remember the article itself now, but it's probably helpful. So if you want to go check it out and maybe get some more explanation as far as this stuff goes, go check out this this article here. Okay, so we talked about the problem. We said we can fix it with momentum. What is momentum? So we'll go back to the formulas that we've kind of been using before. So the gradient, right? And then before we had this eta here, or an eta value here, and we had x minus that, because we had inputs, or the weights, minus this basically update term, we'll call it. But now we've added this new piece, we added this new piece called momentum, and then we've also changed the parameter update function. So if we just to compare, if we look at, let's see, I don't have it listed there. Let's go back to let's go back to gradient descent for example. Okay. Damn, where did I put it? Here. Sorry, guys. Here. This is so this is what we started with. Okay. And now we are going to momentum. And as you can see, we added a couple things. So we've added this momentum term. We've changed the parameter update. So basically, what we're trying to do here is we're trying to take the moving average of the current gradient with the previous gradient. Okay. And what that's going to allow us to do is we're not going to update now based just solely upon the parameter. We're going to update on the parameter and what came before. So for example, if we were cruising along, making some good progress before, and all of a sudden we run into some resistance or we stop, then that past term is going to help us push through or help us still update more heavily than what we would have otherwise, and it'll keep us from getting stuck. So that's really the idea behind it. And then again, so this is this beta is just the I believe it's the decay term. Sorry, the decay rate. Excuse me. So this just determines how much weight we're going to give the gradient versus momentum. And if b is 1, then we're going to be using we're only going to be taking into account the past terms. We don't care what the actual gradient is. We only care what the past one was, and vice versa. If we b is 0, then it's the same exact thing as stochastic gradient descent. We don't use this momentum parameter at all. So there you go. That's a brief summary, and this v is it's a way to weight how much of the gradient is actually applied versus how much of the momentum is applied when updating the parameter. This is, and I may have misspoke earlier, this is how we decide how much weight of the gradient versus the previous to assign to the momentum parameter. And this is the way we assign how much of that is actually going to go into updating our values. So, v and b are similar, but not the same. And just also to kind of in the same way that, if this is 1 or 0, we either have SGD or full momentum. Well, in this case, if v is 0, the algorithm becomes the original SGD. And then with 1, it becomes, we only factor in the momentum. So it's two ways of tuning, and they provide slightly different results. They're similar, B and V, but they have slightly different impacts, and we'll show that in a bit when we actually hop into the code. Okay. So just as a recap, we are looking at this perceptron code, and we're looking at SGD, and we want to put momentum. So again, we have a video on that. I have another series on neural nets from scratch, which talks all about perceptrons and how they're built. So I won't really go into a whole lot of detail about the mechanics of that. And then we have another video in the series, the last video on SGD. So I'm not going to go super into all the things we've already talked about in that video. So really, in this part, we're just focused on how can we implement momentum in the code we've already got. So same thing. We have our imports here. We're initializing our data. This is kind of the same as the last. We're just initializing this as an array. We're taking our x values here. So the first 3 columns are x, and then the last columns are target y. We're initializing our weight matrix, or our b matrix, or inputs. There's a lot of different ways you can call this, but we'll call it weights here. Again, we're finding SST, the sum of squares total. I'm not going to go over that. We've already done it in the past video. And assigning batches, again, already covered that. Getting values to batches, already covered that in SGD. Calculating the gradient. This is where I made a change here. So last time we were calculating, excuse me, let me adjust my chair. we were calculating the gradient and updating the parameters all in a single step. But now as things have gotten more complicated, it's actually more beneficial to calculate the gradient in its own step and then update the parameters as a second step. So just keep in mind we've just taken out the part where we update in this function. So now it's only calculating the gradient here. So we're calculating the gradient and we're returning SSE, similarly to the other function we created in the last video. And we're setting our hyperparameters in the same way. So we're setting our weight vector equal to new parameters, so we don't have to reinitialize the loop every time. And then we're setting a list to hold our values we're interested in. We're getting our SST only once. We're setting max epochs to 100, or I guess in this case max iterations. Either way you want to call it. Batch size is 5, and again we can test different batch sizes. In this case 2 and 5 work well because we only have 10 rows of data, but in theory, for a real life problem, we could adjust this to any, and that's actually should be scalable to any problem, even if it's not easily divisible. It should make a batch size with the remainder, is how this code is set up to handle that. Learning rate is set to 1, so basically we're just not setting it right now. And these are our two new parameters, so beta and new. And so this was the earlier in our code, but I believe it's actually called new, or at least in the textbook I'm following, it's called new. Okay, so how do we actually plug this in? So same thing. The outer loop handles our epochs, our iterations. We're making a list of what we want to include, of what data instances we want to include in each mini batch. We're initializing a momentum list because we need the current gradient, or I'll call it the current gradient, and then the momentum is the previous gradient. So we need to keep a list of all of the momentum values so we can grab the previous one for updating. And then we want to increment at 0 because we need to do something different on the first iteration versus the others. So we'll just initialize a incrementer so we can use this if-else statement to handle that part of the logic. We're iterating through the batches. So for every batch in this list, we're going to go through. We're going to get our actual values for the x and for the y. We're going to plug those values into the calculate gradient function, which we looked at earlier. It's going to spit out our gradient and our SSE term. And then now, this is the new part. This is the part that handles this. So that part handles the new piece of our function. Okay. So basically all we're saying is if 0, we don't care about the previous momentum because we don't have it yet. We haven't had a previous momentum to factor in, so we're only going to take into account 1 minus beta versus the gradient. Okay, so that's how we're handling the first value, and in this case it's just easiest to make it its own piece of logic. So we'd use an if else. There's probably a different way to handle it, but that was just easiest for me. And then now for every other time that we iterate through this, we want to look at the previous momentum value, and we want to factor that in when calculating the current momentum value. Okay, so that's why we're looking for this is why we keep it as a list, so we can look for the increment -1. So the place we are currently -1 gives us that previous momentum value. Okay, and then we append that to the list again, so we have the previous and the current. And then when we're actually updating our parameters, this is let me back up. This is the next part of the equation where we actually update the weights, and that is synonymous with this piece right here. And in this piece, we're saying, okay, we're updating our parameters, our weights vector. Similarly in the past, the only difference is we're adding on some more complexity here with the news, but It's still, the weights minus the learning rate, and then this update term. And now the update term has been complicated to include a 1 minus new term, by the gradient plus the new new by the momentum, or like our current momentum. Because remember, like, we wanted to update with the past one, but we want to use the current momentum to update our weights. Because, let's see, let me go back up to the formula. This one updates with the previous momentum to get our current, and then we use our current here. So hopefully that makes sense to you guys. And like, again, as always, if it doesn't make sense, drop me a comment and I'll try to like find some way to show you this visually, so we can see what's actually going on here. But hopefully this should make sense. But anyway, just let me know if it doesn't. And then finally, like in the past, we're appending all of these things to lists so that we can actually plot them. And let's clear everything so we can rerun it. Ooh, let me select a kernel. Let's run. Might take a minute for it to load. Should have done it beforehand, but all right. So there we go. As we can see, we still have some of that noise, but we are converging, and we're converging quickly. I mean, it's hard to tell, honestly, in this case, if this is doing any better than SGD, because we have a small data set and a small number of iterations. But and also it could be in this case, because honestly to me it doesn't look like it's doing much better. But it's maybe because we haven't tuned this correctly. So for example, we haven't tuned beta or new, or what, all these parameters that we can adjust, we haven't tuned them correctly. So another benefit is this gives us more tunable parameters than SGD. So we can adjust these, and hopefully that will push us to converge faster. So one of the things we can do is we can set new higher, and hopefully that will help us converge a bit faster. Maybe slightly. Let's just, for giggles, let's put this at 0.1 and see how that goes. And you can try all, you can try all kinds of combinations. Okay, so there we go. We're converging pretty fast on that. Let's see if we, just put it at 0.1, what happens? Okay, there we go. That's pretty quick convergence. Actually, I would say that might be better and less noisy, or it cuts the noise a bit. So, again, play with it. You can play with it. You can also change the batch size. You can change it to 2. Now, that should give a whole, this actually probably make it way more noisy if I had to get, yeah, see, way more noisy, because we have a lot less data points, included in the batch size. So anyway, again, guys, just something to play with. You can play these parameters, but this is the crux of how this momentum value works. We're just trying to, we're trying to give precedence to the gradients that happened in the past, or that worked well in the past, to help push us through to the future. Well, it sounds like a quote from a book or something, but anyway, that's the point, and it's just trying to help us push us down the slope faster, so we can get down here and we can really get close to the optimum solution as fast as we can. And then also, if we get stuck somewhere, it helps us bust through that local optimum, so we can bust through and find the global. Okay, so that's pretty much it for SGDM. Like I said, if you had any questions, just leave them in the comments and I'll get to them. And again, guys, if you like the content, as always, please consider liking and subscribing, and I'd really appreciate it. It helps me produce better content for y'all, and it helps me going forward, and especially the comments, figuring out how to make better and better videos for you guys. So again, leave me some comments, like, subscribe, and thank you guys again so much for watching the video. I hope you have a great rest of your day.